Okay, in this problem, we have several pieces of information. We have a crew of 8 can row 20 kilometers per hour in still water. The crew rows upstream and then returns to its starting point in 15 minutes. If the river is flowing at 2 kilometers per hour, how far upstream did the crew go? Okay, it's important to recognize that how far upstream did the crew row is the final question, the ultimate question, if you will. But let's draw a few pictures and see if we can see what this means. Okay, obviously we have a river. Here's my beautiful river. We can even add, some blue color in there for you. Okay, here's the river. A crew can row 20 kilometers per hour in still water. So the crew's rate is 20 kilometers per hour. And again, I'm just reading through the problem and making notes. So the crew's rate is 20 kilometers per hour. They row upstream and then back downstream in 15 minutes. Up plus down in 15 minutes. If the river is flowing at 2 kilometers per hour, how far upstream did the crew go? Okay, so we know that no matter if the river is flowing this way or if the river is flowing this way, it's going to be working with them at 2 kilometers per hour in one direction, and actually they're going to be fighting that current when they're coming in the other direction. So ultimately, you can just assign the river a flowing direction. So for us, we'll say the river is flowing in, and let's use a different color. The river is flowing, here we are. The river is flowing in that direction at 2 kilometers per hour. So we want to know how far upstream did the crew go. Okay, so we have distance 1 plus distance 2. Okay, and then we have time 1 plus time 2 equals 15 minutes. So their time up the river plus their time back the river totaled 15 minutes. So we write that down. Let's see, what else can we pull out of here? Well, we know that there's a rate going, so rate upstream would be 20 plus 2, right? Assuming the river's, again, the river's rate is going with them. So they can row at 20 kilometers per hour when nothing's moving. So they have their rate, how fast just them can go, and then the river is sort of pushing them or helping them along. So the rate upstream is 20 plus 2. So then their rate downstream is actually going to be 20 minus 2, because when they're coming back down the river, they're fighting this current, right? So the river's pushing them this way when they're trying to go this way, so that takes away from their overall rate. So we use subtraction in math to show that. So their rate up is 22, and their rate down would be 18. Yeah, I did that right, 18. So we know that distance equals rate times time, and we know that distance up equals distance down. And notice I'm using 1 and 2 here, but you could use, up and down. Either one works for me. So you have distance equals rate times time. Let's free up a little space here. Hopefully, where do I want to free up space? We'll make the river just a pinch shorter. How about that? Okay, give me some writing room. So here we are. We operating off of this. Then we know that distance 1 equals rate 1 times time 1, and distance 2 equals rate 2 times time 2. Ultimately, if we say distance up is distance 1 and distance down is distance 2, then according to our ultimate question over here, we're only interested in distance up. But we know that distance 1 plus, time 1 plus time 2 equals 15 minutes. So we can solve that for time 1, and we say, okay, time 1 then equals 15 minus time 2, but that requires us to find time 2. So since we don't know the numerical distance, what we actually do is we're going to set rate 1 times time 1 equal to rate 2 time 2. Since this equals that, we can replace rate and time in this equation over here, right? So so that's what we do. And again, let's move over to a new page. Don't worry, I can flip back to this at any time, but we're going to move forward for just a second and say, okay, we know that distance 1 equals distance 2, so that means rate 1 time 1 equals rate 2 time 2. Again, we said that rate 1, which was the distance up, rate 1 was 22, and time 1 was equal to t2 minus 15, or no, other way around, 15 minus t2, because t1 plus t2 equaled 15, so t1 equals 15 minus t2. So we write that over here. 15 minus t2 equals rate 2, which we said was 18 because they were fighting the current then, times t2. So now we solve for t2, and 22 times 15, 10, 11, 2, 2, 0, 3, 3, so 330. 330 minus 22t2 equals 18t2, and I'm just doing algebra steps here. Add this to both sides because I want to combine like terms, and that means that 330 has to be equal to 18, 8, 9, 10, carry the 1, 2, 3, 40 t2. Divide both sides by 40, and let's see, 2, 3, 4, 6, 7, 8 is going to get me closest, I think. 8 would be 320, so that leaves 10, so it's 8 1/4. So time 2 equals 8.25 minutes, and that 0.25 just comes from the fact that 1/4 as a decimal is 0.25. So then, going back to our original equation here, we can say then that the distance 1, which is what we were trying to find, is going to be equal to rate 1 times time 1. So distance 1 equals 22 times 15 minus 8.25. And remember, we said, where is it? Come, highlighter. We said time 1 is equal to 15 minus time 2, and we found time 2 to be equal to 8.25. So we plug that into our distance 1 equation and solve. So 15, we'll give it some decimals there, minus 8.25, this is going to be 7.5, and then 15, 8, 9, 10, 11, 12, 13, 14, 15 would be 7. So 22 times 7.75, we come over here, let's go ahead and add decimal and make life a little easier. 10, 11, 0, 4, carry the 1, 14, 15, and then 0 again, 14 and 15, adding all that together, 4, 5, 9, 10, 5, 6, 7. We have 1, 7, 0, 5, 0, 0, and we have 1, 2, 3 decimal places, so we go 1, 2, 3 decimal places. So the distance, all total, distance upstream equals 170.5, and I actually don't remember the units, So let's go back and check. Wait, come back. Kilometers, yes. So we can say that our final answer to our ultimate question is 170.5 kilometers.